In this video, we want to learn how we can find limits at infinity. Let us start with this simple but very important example. We want to find limit of 1 over x as x approaches positive infinity and also when x approaches negative infinity. Limit at infinity means that x becomes larger and larger. So, maybe it's not a bad idea for finding limit at infinity to substitute big values for x to see what is the value of the function. For example, you can choose 100, 1000, 1 billion and substitute those values for x to see what is the value of this function. For example, if you substitute 1000 here, this would be 1 over 1000. 1 over 1000 is 0.001. It's a very small number. This suggests that this limit should be 0, which actually it is. This limit of this function when x approaches infinity is 0. When x approaches negative infinity, same way, you can substitute large numbers but negative large numbers like negative 1000, negative 1 million, negative 1 billion and so on. For example, if you substitute negative 1 million here, 1 over this would be negative 0.000001, which obviously it's very small number. So this suggests that this limit when x approaches negative infinity is also 0, which completely makes sense. When we have fraction and the denominator of the fraction becomes larger and larger, the value of that fraction approaches 0. Also, if we look at the graph of the function y equals 1 over x here you can see the graph of 1 over x. When x approaches positive infinity or when x approaches negative infinity, in both cases, something happens. When x approaches positive infinity, the y value of the function approaches 0. For example, suppose here is a large number. As you can see, the y value of the function is very small number. So as you can see, when we go far to the right, the y value of the function gradually approaches 0. The graph of this function approaches 0, approaches the x-axis. Also, when we go far to the left, the y value of the function is negative but very small negative number. This distance between x-axis, and the graph of the function is the y value, and as you can see, it's very small number. So the graph of the function also confirms our result. So finally, limit of 1 over x when x approaches infinity or negative infinity is 0. Now we use this fact for finding other limits. So let me write down this general rule or law for ourselves, and it helps a lot for finding these type of limits. Keep this in your head. When x approaches positive infinity or negative infinity, doesn't matter which one, as long as x approaches infinity or negative infinity, limit of any number, so here can be not only 1 like here or here, limit of any number over x to the power of n. So again, not only x, maybe x to the 2, x to the 3, x to the 5, x to the positive powers, even the power can be decimal, x to the power of 1.5. Limit of any number over x to the n as x goes to infinity is 0, which completely makes sense, and it's obvious because numerator of this fraction is just a number, but the denominator involves x. And what is x? Infinity. So if you divide a number by infinity, what do you expect? 0. Because when you divide something by infinity, you divide it to infinity piece. So each piece is very, very small. So in another word, the limit is 0. Keep this fact in your head, and it helps a lot to find these type of limits. For example, let's say we want to find limit of 2 over 3x plus 5 when x approaches infinity. Based on this rule, you don't need to do anything. Just you can simply say the numerator is a number. The denominator involves x, and x is infinity. 3 times infinity, 3 times x, plus 5. You can ignore 5. And if you add 5 to the infinity, it's also infinity. So we have a number over infinity. Any number over infinity is simply 0. And if you needed to show your work for these type of limits, in a moment I will show you how you can show your work to find these type of limits. But this is a very simple basic example. Look at the other one. What is the limit of negative, let's say for example 10 over, so this is 10 over 5x2 plus 1. A number over x to the 2. You can ignore this 1, and 5 times x2 is infinity. So again, we have a number over infinity. So the limit is 0. So as you can see, this rule is very helpful. Any number over x, or x to the 2, or x to positive power is 0. Now, let's work on more examples that directly we cannot find those limits by that rule. For example, look at this limit. What is limit of 3x2 minus 5x plus 1 over 2x to the 2 plus 7x plus 10 as x approaches infinity? There is a general method for finding the limits of rational functions. This is an example of a rational function. In numerator we have polynomial, in denominator we have polynomial, and for finding these type of limits, there is a general method. For finding these type of limits, simply you have to divide. So let me write down the rule here. Simply always divide every term in the top. So divide the top. So divide numerator. So it's better to say it this way, numerator and denominator by highest degree of denominator. So just you need to look at the denominator and find the highest degree of the denominator. If you look at the denominator, we have 10, we have a 7x and 2x2. Between these terms, of course, this term has the highest degree. The degree of this term is 2. So you have to divide every term in the numerator and every term in the denominator by x to the 2. So you have to divide the numerator and denominator by x to the highest degree of denominator. So x to the 2 in this case. Let me show you how this method works, and it helps you to find these type of limits easily. So let me start from here. So we are going to divide every term in the numerator by x2. And also we divide every term in denominator by x2 because we don't want to change anything. So whatever we do with numerator, we do with the denominator. So then we have something like this. 10 over x2 as x goes to infinity. And if x goes to negative infinity, we are going to do the same. The method is the same for infinity and negative infinity. Now, if you simplify these fractions just a little, we would have what? Because there is x common between numerator and denominator, we can simplify them. For example, what is 3x to the 2 over x2? x2 and x2 cancels. So this term is just 3. Here, the numerator is x to the 1. The denominator is x to the 2. X to the 1 with x to the 2 cancels. Only one x in the denominator. We have minus 5 over x. The next term would be the same. It doesn't change. Now look at the denominator. 2x to the 2 over x2 is 2. Then 7 over x and 10 over x2. After you did this, now you need this general rule. This helps a lot. I told you, limit of any number, 2, 5, negative 2, over x to different powers as x goes to infinity is 0. Now look at here. In the numerator, we have negative over x. What is limit of that when x goes to infinity? 0, because we have a number over x and x goes to infinity. So the limit of this is 0. So this is 0. This is also 0. 0 and 0. So, because x goes to infinity, all of these fractions are 0. Just in the numerator, then we have only 3. And in the denominator, 2. So what is the limit? 3 over 2. And again, if this limit was x goes to negative infinity, the process is always the same. And the result, the answer of this limit would be also the same in this case. But let me show you another example. Now look at this. We want to find limit of negative 2x to the 3 plus 4x over x2 plus 9x plus 100, and x approaches negative infinity. What was the rule for finding limit at infinity of rational functions? Simply divide the numerator and denominator by highest degree of denominator. And in this case also the highest degree of denominator is x to the 2. So we are going to divide every term in the numerator and every term in the denominator by x to the 2. Then we have negative 2x to the 3 over x2 plus 4x over x2. x2 over x2, 9x over x2, and 100 over x2 as x approaches negative infinity. Now let's simplify the fractions. Negative 2x to the 3 over x to the 2 is negative 2x. x2 from the bottom with x to the 2 from the top cancels. Just one x we have in the numerator. The next fraction is 4 over x. Now focus in the denominator. x2 over x2 is 1. Then we have 9 over x and 100 over x to the 2. Can you find the limits that are 0? Limit of 4 over x. Limit of 4 over x, 0. 9 over x, 0. And 100 over x2 is also 0. But this is a bit different than the previous example. Here we have this term here, which is not 0. We have negative 2 times x, and x goes to infinity. So basically these limits, limit of 4 over x, 9 over x, 100 over x to the 2 are 0, but we have still this negative 2x. So finally, what is this limit? Now here, if you attention a little, we have in the numerator negative 2x, and in the denominator we have 1. And attention, x approaches negative infinity. X is a very, you can imagine it this way, it becomes larger and larger, but to negative infinity. If you multiply it by a negative, it would be positive infinity. So limit of negative 2x when x goes to negative infinity is positive infinity. So the numerator approaches infinity This is 0. Forget this. Infinity. The denominator is just this 1. And infinity over 1 is infinity. So this limit equals infinity. Now look at the next example. What is the limit of 4x plus 7 over 2x to the 3 plus 7x minus 10 as x approaches infinity? Remember, divide every term in numerator and every term in the denominator by highest degree of denominator, which is x to the 3. So then we have 2x to the 3 over x to the 3 plus 7x over x to the 3 minus 10 over x to the 3 as x goes to infinity. Let's simplify. 4x over x to the 3 would be only 4 over x2. 7 over x to the 3. In the denominator we have only 2 plus 7 over x2 minus 10 over x to the 3, and x approaches infinity. Now, if you pay attention, what is this limit? 0, because we have a number over infinity. 0 also here. This is also 0. This is also 0. So numerator is simply 0. What is denominator? Only 2. What is 0 over 2? 0. So this limit equals 0. Let's review these 3 examples that we did here with this rule. For finding limit of rational functions, we divide numerator and denominator by highest degree of denominator, and then we can find the limit. Before we do more examples and we will learn more about this technique and other things, let me show you a shortcut method for finding these type of limits. But if you are asked to show your work, of course, this is the better way. This long solution is the better way. But if you want to find the answer a bit faster, actually more faster, a lot faster, this shortcut would be really helpful. And also you can use this shortcut to check your final answer, to make sure the number that you find here, in this case 3 over 2, is right. Let me show you the shortcut method. It's really helpful. When x approaches infinity, attention, you can use this method only for limits that x approaches infinity or negative infinity. When x approaches infinity, usually we have a bunch of terms in numerator and denominator. Only you can keep, and you have to keep, the dominant terms in numerator, the terms that are significant in the numerator and denominator, and ignore and delete other terms. What I mean by this? For example, in this case, if I want to find this limit, because x approaches infinity, of course 1 compared to things like x and x2 is nothing, because x is infinity. When you have 5x, which x is infinity, 1 can be ignored, because 1 plus infinity is also infinity. So you can obviously ignore this one. And when you have something like x to the 2, then you can ignore also 5x, because this is x to the 2, infinity to the 2. This is infinitely bigger than the other terms. This x2 is infinitely bigger than x. So you can ignore not only 1, also 5x. So what remains in numerator? Only 3x to the 2. And you can ignore other terms. So just we keep the dominant terms in numerator and also in the denominator. What is the dominant term in this case, in denominator? It should be clear for you, 2x to the 2. Now if you simplify x to the 2 from the top with the bottom, what is this limit? 3 over 2. Look at these two answers. They are the same. I know this method is shorter, faster, easier, But if you want to show your work, you have to use the other method. Now let's try this example. We want to find limit of this expression when x approaches infinity. Similar to the previous question, we are going to keep the dominant terms in numerator. What is the dominant term? Between negative 2x to the 3 and 4x, the one with higher degree is dominant. So negative 2x to the 3, and in the bottom just x2. If you simplify this, then you have limit of negative 2x, x to the 2 from the top with bottom cancels, and negative 2x, x to the 3 over x to the 2 is simply x. So this would be limit of negative 2x as x approaches negative infinity. And now, what is this limit? Look at this. It's similar to what we had here. Same thing. X approaches negative infinity. And we have a negative 2. Because x approaches negative infinity. But if you multiply the infinity by negative to negative infinity by negative 2, so the limit of negative 2x when x approaches negative infinity is positive infinity or infinity. So the limit is infinity. Again, look at the answers. Obviously, they are the same. And let's try the last example that we had here. We want to find limit of this function when x approaches infinity. Just keep the dominant terms like this. Simplify. 4x over 2x to the 3 would be 4 over 2x to the 2, or you can say 2 over x to the 2. I prefer to keep it this way. 4 over 2x to the 2 as x approaches infinity. Or actually, why not to simplify it completely? It would be only 2 over x to the 2. As you can see, you have a number over infinity. X goes to infinity. Do you remember the important rule when we have a number over infinity? What is the limit? A number divided by infinity is 0. The limit is 0. It's not right to say a number divided by infinity. Infinity is not the number, so we cannot divide really by infinity. We can divide number by number, not number by infinity. But we can say limit of this is 0. So as you can see, the shortcut method is really helpful, at least to check your answers. Now you know this answer is right. But the shortcut method is faster, easier. Let's do another example with the shortcut method and the long method. Look at this question. We want to find limit of x approaches infinity of this 2x minus 3 to the power of 2 over 3x plus 1 times 4x plus 5 as x approaches infinity. Here, it's not completely clear that what is the highest degree of denominator. We know that for finding these limits, we have to divide the numerator and denominator by highest degree of denominator. Actually, you can simply find the highest degree of denominator here. Look at this bracket, you have 3x. Look at the other bracket that multiplies by this, 4x is the highest degree of x. So of course, by multiplying this 4x in 3x, we can find the highest degree that can appear in the denominator, and it would be 12x to the 2. So for finding this limit, we have to divide every term in numerator and every term in denominator by highest degree of denominator, which is x to the 2. So we have to divide everything by x to the 2. But before doing that, we have to expand the brackets. We have to FOIL them. And also, you have to expand 2x minus 3 to the 2. If you don't know how to do it, if you don't know how to find this, if you know the identity for that, it would be great. If you know the identity a minus b to the 2 is a2 minus 2ab plus b2 is great. But if you don't know, no worries. Simply you can say 2x minus 3 times 2x minus 3 and then FOIL them, expand them. 2x times 2x is 4x to the 2. This multiplies by this. Then negative 6x and another negative 6x from here, and finally 9, which if you simplify this, here we can write limit of 4x to the 2 minus 12x plus 9, because negative 6x and negative 6x is negative 12x. Now in the denominator, if we do the same, if we multiply the bracket by the bracket, we have 12x to the 2, 15x, 4x, and 5 as x approaches infinity. 15x and 4x, if we add these two, is 19x. So simply we can write 19x plus 5. Now is the time to divide everything in the numerator and everything in the denominator by x2. So then we have 4x to the 2 over x to the 2 minus 12x over x to the 2 plus 9 over x to the 2. And in the denominator we would have this 5 over x to the 2 as x approaches infinity. And if you simplify, you have 4 minus 12 over x plus 9 over x2, and in the denominator you have 12 plus 19 over x plus 5 over x2 as x approaches infinity. Remember the rule: when we have a number over x to the 2, things like that, all of those things are 0. So this is 0, this is also 0, this is 0, and this is 0. So what remains? Only 4 in numerator, 12 in the denominator, so the limit is 1/3. But let's see how we can find this limit with the shortcut method, with the method of considering and keeping the dominant terms in numerator and denominator, keeping the terms that are significant, the terms that are really important. In numerator, look at the numerator. We have 2x minus 3 raised to the 2. To find the dominant term here, between 3 and 2x, which one is significant? Of course 2x, because x, it involves x, and x is infinity. So just keep that 2x and raise it to the 2. Ignore that negative 3. Done. Now look at the bottom. In each bracket, keep the dominant terms and ignore small terms, 3x and 1. Which one is important? 3x. So just keep the 3x, and in the other one 4x, and x goes to infinity. Don't forget to write the notation of limit here. You should not forget to write this. All of this is right when we do limits. 2x to the 2 is 4x to the 2. Don't forget to raise these 2 to the 2. 3x times 4x is 12x to the 2. x2 from the top and x2 from the bottom, they cancel each other. So what is the limit? 4 over 12. 4 and 12 cancel each other, and the limit is 1/3. Same answer, but shorter and faster method. Now look at this important example. Limit of square root of 4x to the 2 plus 5 over 3x plus 2 as x approaches infinity. For finding this limit, like other limits in the rational form, we are going to divide numerator and denominator by highest degree of denominator. And attention, highest degree in the denominator is x to the 1, so we are going to divide everything in the numerator and everything in the denominator by x. The denominator is going to be 3x over x plus 2 over x. But for numerator, because of that radical, we cannot simplify it right away. I am going to write it as this: radical 4x2 plus 5 all over x. Now for simplifying the numerator, you need to remember some properties of the radical. Let me show you what properties you need to remember. If you have radical A over radical B, to separate radical. If you want to divide a radical by another radical, you can simplify it and write it as radical A over B. This is one of the properties that you need to remember. The other thing is that if you have x, you can write it in a radical form like this, radical x to the 2. It's obvious that you can write x as radical x to the 2. But attention, this rule that square root of x to the 2 is equal to x is not always true. This is something that many students forget to consider. This is true only if x is greater than equal 0. Otherwise, it's not true to say radical x to the 2 is x. We will discuss about this when x is negative later in this video, because we need it for another question. But for now, let's back to our question to complete our solution. Now, to simplify numerator, I am going to rewrite the x in the denominator, this x here, in a radical form. So, I am going to write x as radical x to the 2 in the denominator, and let's write the numerator, 4x2 plus 5. 3x over x in the denominator is just 3, and 2 over x is 2 over x. X goes to infinity. I am not going to simplify the denominator right now. I know the limit of 2 over x is 0, but let's keep it like this for now. Now, I am going to merge this radical with this radical. I want to combine these two and write it as a single radical, based on this rule that here we learned. So we can write the numerator like this. Limit of, put a big radical here, 4x to the 2 plus 5 over x to the 2. And the denominator is 3 plus 2 over x. Now, divide every term in the numerator here, this term and this term, by x to the 2. Separate the terms. Actually, let's do it here. So we have 4x to the 2 plus 5 over x to the 2. I am going to rewrite this as 4 plus 5 over x to the 2. We had this 4x to the 2 plus 5 over x to the 2. What I did here was that I divided this by this, 4x to the 2 over x to the 2, 4x to the 2 and x to the 2 cancel each other, only 4 remains, and 5 over x to the 2. So we got this. Now, probably you remember the important rule that we have learned in the beginning of the video. When x goes to infinity, when x approaches infinity, any number over infinity is 0. So this is 0, and also 5 over x to the 2 is 0 when x goes to infinity. So in the numerator we have only a square root of 4, which is 2, and in the denominator we have 3. So the limit equals 2 over 3. So the limit of this expression when x goes to infinity is equal to 2 over 3. Now look at this example. What is limit of a square root of 4x to the 2 plus 5 over 3x plus 2 if x approaches negative infinity? Here we have same expression, but x approaches negative infinity. The process of finding this limit is similar to the when x approaches infinity, but there is a little difference, and it's really important. We are going to divide numerator and denominator by highest degree of denominator as usual. So it would be limit x approaches infinity, 3x over x plus 2 over x, and in the numerator we have radical 4x to the 2 plus 5 over x. Now let's back to here. Do you remember here I mentioned that radical x to the 2 is x when x is greater than or equal 0, and in general this is not true for every x. Now we want to talk about this. If x is negative, if x is less than 0, then what happens? If x is less than 0, it is not true to say x is radical x2. Let me show you why. It's better to learn why this is not true if x is less than 0. For example, imagine a negative number. Consider any negative number you want. For example, let's say negative 3. So, we suppose x to be negative 3. Let's see what happens if we plug in negative 3 here and here. We want to check, is x equals radical x to the 2 even for negative numbers or not? I am saying no, it's not true. Let's see. If x is like negative 3, let's see what happens. So I am going to replace x with negative 3. If we plug in negative 3 here and negative 3 here, negative 3 raised to the 2 is 9 and radical 9 is 3. But in the other side is negative 3. Is 3 equal to negative 3? Of course no. So this shows that we don't have this rule for negative numbers that x equals radical x to the 2. But if we want to keep it, how we can fix this? Basically, radical x to the 2 equals negative x if x is less than 0. By putting this negative, we can solve that issue that we had. So radical x to the 2 is equal to x if x is greater than or equal to 0. But if x is less than 0, radical x to the 2 is negative x. Or in another way, we can say, or x equals negative radical x to the 2. If you multiply both sides of this relation. So this relation is true. If I want to make this side x to get rid of this negative here, if I multiply both sides of this relation by x, I can give this negative to the other side. So x is negative radical x2. X equals negative radical x to the 2 if x is less than 0. So x equals negative, attention, negative radical x to the 2 if x is less than 0. So now we have this important rule, and it's good to keep it in your head forever, that x is radical x2 if x is positive. If x is negative, x equals negative radical x2. Or you can remember it this way, radical x2 is negative x. Maybe this one is better. It's up to you, but keep it in your head. Don't forget, this is true if x is less than 0. Then we have this rule. Now let's back to our question. Here in this question, x approaches negative infinity. I forgot to put negative here. X approaches negative infinity. So x is not positive, x is negative. So you cannot say x is radical x2. X is negative radical x2. So instead of this x here, you have to replace it with negative radical x2, not like the previous question, radical x2, negative radical x2. So this is really important. Then we have radical 4x to the 2 plus 5 over negative radical x2 all over 3x over x plus 2 over x. As x approaches negative infinity. Now if we simplify the denominator, we have 3 plus 2 over x, and in the numerator, don't forget that negative should stay outside of the radical. Negative, now I want to merge these two radicals. So I have then 4x to the 2 plus 5 all over x to the 2. If we divide the terms in the radical, we have radical 4 plus 5 over x to the 2. And in the denominator we have 3 plus 2 over x as x approaches negative infinity. Now here 5 over x to the 2 is 0. The limit of this when x approaches infinity, this is 0. This is also 0. In the numerator we have negative radical 4, and in the denominator we have 3. So the limit is negative 2 over 3. So the limit of this function when x approaches negative infinity is negative 2 over 3. But the limit when x approaches positive infinity is 2 over 3. So as you can see, the limits are different when x approaches infinity and negative infinity. One of them is 2 over 3, the other one is negative 2 over 3. And the important thing that you have to learn in this question is basically this rule here. Radical x2 is not always x. Depends to x. If x is positive, it equals x. If x is negative, it equals to negative x. I hope you liked this video. If you like this video, please subscribe in my channel and see you in the next videos.